All right, we're going to start here in 6.1. First math section. Here we go. So this first section, we're going to be looking at volumes. And this section is going to have to be broken up into multiple videos because it's quite long, and I would like for my videos to be around 10 minutes, if not less. So this first section, we're going to be finding volumes using what we call cross sections. So here we have this bone-shaped solid, and you can see the blue plane that is intersecting this solid here where it's perpendicular to the x-axis, and it creates this outline. This outline is what we're going to call a cross section. So just reading the definition here, a cross section of a solid S is the planar region formed by intersecting S with a plane. So that's what we get here. Now, maybe what you remember back from geometry is that if you have some kind of solid where the base of that solid is the same cross section for the entire height, then all you need to do is take the area of the cross section and multiply it by its height to get the total volume. We're going to be doing it the same way here. It's just that the cross section changes as we move through our object. So here you can kind of imagine if I move this plane through my object, my cross section is going to change as I progress through it. So to fix that, so that we can actually find the volume of the object, we need to come up with a function of the cross-sectional area as we move from A to B along the x-axis here. So moving on to the next page, you can kind of see a little bit more of these cross-sectional areas as we move. There's a lot of jargon going on behind the scenes here, and I'm going to try to explain it as best as I can just by looking through the book here. Basically, what we're going to do is we're going to take this interval from A to B, and we're going to break it up into a bunch of different partitions. Partitions are just tiny little increments of this interval. Here you can see one of the partitions. This is the partition from x k minus 1 to x sub k. These are theoretically so close together that the cross-sectional area from one to the next is pretty much identical. Because it's pretty much identical, we can find the volume in just this one partition by finding the cross-sectional area at one of these guys and then just multiplying that by the height, which is the distance between the two. That'll find the volume of this one partition space. Then if we add up all of the partitioned volumes, we'll find the volume of this total solid. So that's kind of what's going on here. So this is the volume of just one of the partitions, the area of the cross section at one spot, times the distance between the two x values. Then to find the total volume, we just add up all of these individual volumes. Okay, this is where the calculus comes into place. Anytime you have a finite sum like this, and then you take the index values going to infinity. So if we had n partitions on my interval here, think of it like now I have an infinite number of partitions. An infinite number of partitions means that the distance between these two is infinitesimally small. Anytime we're talking about infinitesimally small or an infinite number of partitions, you can probably remember back to Calc 1, this is Riemann sum stuff. And Riemann sums calculate to integrals. So as we take the number of partitions to go to infinity, that's where my interval comes into play. And this is my first, this is the first formula that we're going to need to know here. So for something for you guys to write down and everything that I just said there, the volume of a solid using what we're going to call the method of slicing. Think of it like slicing bread of some kind of a solid, is found using the following formula. So the total volume is going to be, I'll make this a little bit bigger, the integral from A to B over just the cross-sectional area as a function of x dx. Now this changes, right? As I move along the x-axis, my cross-sectional area changes. To go back over to the book, this is what we were talking about before, right? As I move along the x-axis, the area changes. So if I just integrate over that changing area, that'll give me the total volume. All right, the book gives you some steps here that you can read through with actually calculating one of these, but we're going to jump right into this first question. So this first question A pyramid 3 meters high has a square base that is 3 meters on a side. The cross-section of the pyramid perpendicular to the altitude x meters down from the vertex is a square x meters on a side. Find the volume of the pyramid. Okay, so I moved on to the next page of the book here just because I tried to draw it myself and I didn't like it. But here we go. This is what we want to think of with the pyramid. So the book does something kind of clever. It puts the top of the pyramid here at the origin and the base of the pyramid here at 3. The reason it has it kind of flipped over like that is that way as we move down the x-axis, wherever location we are is going to be the length of the squares. So if we are at location 3, the base of the pyramid, we have a 3 by 3 square as the cross-sectional area. If we are at location 2, we're going to have a 2 by 2 square as the cross-sectional area. If we are at location x, an x by x square at the cross-sectional area. So I kind of already wrote up a little bit because I had to go back on the video, but this is where we're at now. So here we have the formula still. The volume is just the integral over the cross-sectional areas, where for this particular question, the cross-sectional areas are going to be squares as we move up the pyramid, where this is the formula for the cross-sectional area. The area is just the location that we're at squared, since that's the square that we end up getting. Then, to find the total volume, we just integrate over these squares. So our integral is going to be going from 0 to 3, since that's the location of my cross-sectional areas, right? They're starting at 0 and they're going up to 3. And we're just going to integrate over my area as a formula, x squared dx. And then this is pretty simple to do, right? So this is going to have antiderivative 1/3 x cubed. That's going to be going from 0 to 3. So let me see if I can write that out a little bit better. There we go. So plugging 3 into this, 3 cubed is 27, divided by 3 is 9, minus plugging 0 into this, we get just 0. So that comes out to be 9 squared centimeters or squared meters or whatever the units are. So just to go back to the book to make sure we get the right answer, I said squared and look, it's cubed. I'm talking too fast. Right, we're finding volume here, so 9 cubic meters. Okay, I'm going to pause the video here and start the next video. These do get way more complicated, so we're going to do a more complicated one here next.